you through our activity in our final project. And so after the introduction of some key ideas in natural language processing, this activity is intended to guide you through the code we prepared and to introduce latent semantic analysis, as well as illustrating some of the immense importance of singular value decomposition and the process of latent semantic analysis. So as you might have seen already, the majority of the activity involves running code from nlp-_lsa.m, which is this file. And so let's first look at the simple case as a warm-up activity. So what section 1 does is it reads 3 documents and then converts them to a corpora, which is the collection of all documents. After you open all 3 documents, you should first notice that, well, they're pretty short, and then secondly, they contain terms that are drastically different in terms of their topics. So the first document is about pets, the second document is obviously about cooking, and the third document is about artificial intelligence, which are some of the keywords that we have seen throughout the course. So after reading all three of these documents, section 2 converts them to TF-IDF expression, which is something we have introduced you in the background introduction section. And this is achieved with a function called toTF-IDF. It will convert the corpora to a term document matrix, which means for each row it is about a term and each column is about a document. It also generates a dictionary as a byproduct. Well, by definition, dictionary means the collection of all terms that has occurred in the corpora. So if you're interested, you can skim through the function that I've written, and it should be pretty straightforward to follow through. Yeah, so section 3 of the code takes SVD of the TF-IDF representation that we just got, and then it will tabulate the term document matrix and the topic document matrix and the topic term matrix. So let me run those sections. And now, as you might already seen, the topic document table shows that document 1, document 2, and document 3 each has corresponding to one and only one of the topics that we have generated. And notice here the topics we've listed are not completely corresponded to conversational topics in human languages. It is just the name for the intermediate dimensions that we have generated through SVD. So we might call for matrix U, each row is a topic, and each column is a term. For sigma, each row and both rows and columns are topics, and the entries here are the importance of each topic. And for V transpose, each row is also a topic and each column is a document. So here we have topic doc matrix that shows us the relationship between doc 1, doc 2, and doc 2 and doc 3, and the reason they have 0 weights on all the other topics is that they have inherent differences in terms of contents topic, because remember, Doc 1 is about pet, Doc 2 is about cooking, Doc 3 is about artificial intelligence. They have no relation to each other at all, and they have no overlapping with the words that they use. So as you can see in the second table, dog, cat, friend, care is all from document 1. They all correspond to one topic, which is topic 2. And beef, bread, stew, tasty all corresponds to topic 1, which is here, also shown here. And then the rest of the dictionary corresponds to topic 3. So you can also tell by the second table that they have no correlation at all, because these words have very or drastically 100% different meanings in whatever context. So let's move on to the more complicated case, which is our main activity. So section 4 takes all the document we have prepared in the corpora folder, which you can find in here. All the document will be read in and then collected in the corpora, and then section 5 will again convert them to TF-IDF expression. And then we reach section 6. So what's special about section 6 is that it generates a CSV file with the additional documents that we have imported in corpora. So let's run that. So here is the new topic doc matrix, and so as you can see, as the number of documents that we process increase drastically, it's kind of hard for a human being to tell the relationship between each of them just by looking. So this eyeballing method pretty much becomes obsolete for now. We need something more efficient, and that is cosine similarity, which we have introduced as well during the background introduction section. So what this section of code does is it first normalizes each column of the topic doc and topic term matrix, and then take the inner product between each column, and then the result of the calculation should be the cosine value between each of the columns. It also outputs the result of calculation into two .csv files. So here is all the cosine similarity between each pair of the documents, where the rows, where you can subtract the number of rows so that it corresponds to each document. So what we can do now is try sorting by row. Of course, in descending order. So you can see that document 1, 8, 6, 26, 12, 14, they have closest similarity. And if you look at correspondence.txt, you should see that document 1, 6, 8, 12, and 14 are all from the F1 genre. Those are documents that we collected from F1 news. And you can try to do that for as many rows as you want. So if I find the sort the similarity between document 6 and then all the other documents, you can see that it's still successfully sort out the genre it corresponds to. Then we can try some other topics or genre. So document 29. Yep, so document 29, 28, 27, they all correspond to video lecture transcript, which is the transcript that was posted under every video lecture that we have watched. So what I'm trying to tell you is that if you sort any of the rows, the first two documents are guaranteed to be in the same genre that we have provided here. And if you look at the top 5 or top 6 similarities, most likely the documents are from the same genre. Well, you've seen that already. In some cases, you will have a document from another genre mixed into a high similarity column, because that is simply because the wording inside that document has a significant overlap with the wording used in the document that we're sorting on. So that's not something we can control, but if you sort any of the first two columns, it will give a pretty promising result. So the reason behind using cosine similarity is that if you graph the different documents into vector spaces whose basis is topics, in this case we have a two-dimensional vector space with topic 1 being the horizontal axis and topic 2 being the vertical axis, and we have 3 documents, doc 1, doc 2, and doc 3. Each have different weights on topic 1 and 2, but they all have unit length. In such a scenario, doc 1 and doc 2 are considered to be more similar to each other because they have similar weights in both topic 1's direction and topic 2's direction. And this is equivalent to having a small angle between them, and also equivalent to having a cosine value close to 1. In contrast, document 1 and 3 are considered less similar because they have large angle between them and a cosine value close to 0. So that's the reasoning behind using cosine similarity. And then this project only involves a few dozens of documents, but in a industrial level natural language processing project, you can easily come across with thousands of documents, and that is computationally heavy to produce the topic doc and topic term matrices, because they have so many entries. And that is when truncated SVD comes in handy, because we only care about the topics that have large importance in sigma. And as we have learned in the lecture, truncated SVD gives the best low-rank approximation in terms of obedience norm. So by doing truncated SVD, we can keep the effectiveness of classification while alleviating some of the computational stress. So let me just demonstrate that for you. If we open the cosine similarity table generated with truncated SVD, we can do the same by sorting on each row in descending order, while still get pretty ideal result. Well, I'm already using up a lot of time, so I'm not going to show you every row, but you can try that yourself. So truncated SVD is really powerful in terms of saving computational cost while not compromising the accuracy of classification. And last but not least, you might notice that we have a file called preprocessor.m, and that is the preprocessor that we have used throughout the project, 100% coded by ourselves. And to use that, you can, with the preprocessor, you can put whatever original text that you want. You can find any documents yourselves, convert it to .txt form, and then clear out the current corpora that you have in the corpora folder, and then run the preprocessor. It will now generate a new corpora with the customized text that you found yourselves. So if you're interested, you can play with the LSA and preprocessor for a bit. And then one more important thing that we have not shown in the video is that if you put two or at least two sporting genre of text into the original text and convert it to corpora, the accuracy of classification will significantly reduce, because those two genres are both considered to be sports, so that they have a less clear boundary between each other, so that it makes it hard for something like LSA to tell just by their cosine similarity. And that'll be all. Thank you.